Yeah, this room needs it. They keep sticking me in different rooms. If I'm gonna be in here, definitely need another one. All right, let's just start with recap from last time. So last week we started geometry proper. And so we're starting now to develop our axiomatic system. And I told you every axiomatic system is composed of four things. We have our undefined terms, our axioms or postulates, same thing, our definitions, and our theorems. So first off, let's remind ourselves of our undefined terms. What were our undefined terms so far?
Point, line, plane, and between.
Point, line,
And between.
plane, and between. Perfect. And there are postulates so far. So we have postulate group
1.
Postulate group 1. Postulate group 1, what did that tell us?
Talking about there are 3 non-collinear points on the line.
Perfect. There's at least 3 non-collinear points in a plane. What was 1, 2?
The 2 lines created, there are 2 points.
For 2 points, there's exactly 1 line.
If you have 2 points, that implies that there is exactly 1 line to those 2 points. 1, 3 is kind of the counterpart to that one. What does this say?
A line contains at least 2 points.
So if you have a line, that implies that you have 2 points on that line.
Right.
Perfect. And that was it for postulate group 1, right?
Yep, that's everything.
And then we got to postulate group 2,
That's 5.
So postulate 2, what did that say?
A, B, C, then A, B, and C are 3 distinct points on the line.
Perfect.
There is a line.
Not missing anyone. So if you have B between A and C, then that implies that A, B, and C are 3 collinear points, right? Okay. What was 2, 2?
If A, B, C are distinct points on a line, then either A, B, C, B, A, C, or A, C, B.
Perfect. If you have 3 points on a line, then, I'm not sure the best way to say that, you can have A, B, C, A, C, B, or B, A, C. So I've got 3 points A, B, C, not sure what order they're in, but we know over here we have the points A, B, C in some order. Then either B has to be between A and C has to be between A and B, or A has to be between B and C. Perfect. What was 2, 3?
Any 4 points on a line may be labeled A1, A2, A3, A4, so that only between relations are A1, A2, A3, A2, A1, 1A, 2A, 4A.
You're good. Okay.
A1, A3, A4.
So if we have any 4 points on a line, we can label them A1, A2, A3, A4, so that all our betweenness relations are exactly what you read off of here. So that A2 is between A1 and A3, A2 is between A1 and A4, A3 is between A2 and A4, A3 is between A1 and A4. So you can always label your points like those are your only betweenness relations. Okay, 2, 4.
If A and B points are on a line, then there exists CD such that ACB and ABD are infinite. on
Right.
this line. Wrong line.
So here's what it says. We have 2 points on the line. We're guaranteed that there is some point between them, call it C. And we're guaranteed that there is some point beyond them, call it D. And so this is sometimes called the line builder postulate, because once again, I know that B and D are 2 points on the line, so by this same postulate, I know that there's a point beyond them. Okay, here's 2 points on the line. By the same postulate, I know that there's a point beyond them. And so you can recursively use that postulate to keep building out. And it's the same postulate that tells us between any 2 points, there's infinitely many points. If I have 2 points, there's a point between them. Okay, here's 2 points, so there has to be a point between them. Okay, here's 2 points, so there has to be a point between them.
Right.
And you can do that indefinitely. Okay, and then what was 2, 5?
Each line separates the point not on the line into 2 sets if 2.
A line splits the plane. That's essentially what it tells us. If you have some line L, then you split the plane into 3 sets. You have the set of all points on one side of the line, call it capital X. We have all the points on the other side of the line, we call it capital Y. And then we have the points actually on the line, which are not on one side or the other. So the line splits the plane into 2 sides. Right?
Yeah.
And then that was it for those postulates. Right?
And we had some theorems.
And then that's a recap on every postulate we've had so far.
Yeah.
I don't think we're missing, right?
Yeah.
I'll look for it.
Okay. Then last week we ended with,
We started working on
we started talking about what it meant to be inside an angle, right?
yes.
So if I've got some angle here, let's remind ourselves really quick, what's an angle?
An angle is two rays that go.
Two rays. Two distinct rays meeting together at two rays coming from some single point, typically we call them. So here's an angle, right? We mark the sides of the angles, sometimes with that line between, to let us know this angle goes from this side to this side, because sometimes we draw a bunch of angles on top of each other. So that's a common way that we represent the angle. And we talked about the interior of the angle. What was the interior of the angle? The way we thought about this is we said, look, through one of the rays, draw the line, we'll call that line L1. Through one of the rays, draw a line, we'll call that L2. Then the interior, and this ray right here, this was a ray R1, and this was a ray R2.
The interior would be between L1 and L2 and...
But we can't really use between like that. Between is something we say with points.
The interior of the angle are
So they're all the points on the same side of L1 as R2,
and on the same side of L2 as R1.
and on the same side of L2 as R1. So they're all the points in here. Question, is a point actually on the angle part of its interior?
No.
Yeah.
No. Why not? Because those points aren't on a side of the line. They're on the line.
Right.
We said all the points who are on the same side. So here's the line L1. L1 splits the plane into two sides.
Yep.
We're taking all the points that are on this side of L1. So that doesn't include L1 itself. So that doesn't include this ray R1.
Okay.
So that's just the points over here. And on the same side of L2 as R1. That's this side of L2. So we got this side of L2 intersected together with this side of L1. What are all the points that are in both those?
I mean... Say that again. There's the points...
Let's try it like this. Get rid of that for a second. I'm going to draw in all the points that are on the same side of L1 as R2.
Right.
So that's all the points over here.
Yeah.
These are all the points on the same side of L1 as R2, as array R2. Now, I'm going to draw all the points that are on the same side of L2 as R1.
Okay.
That's this side. Right?
Right.
Yeah.
The interior of the angle is all the points that are on the same side of L1 as R2 and on the same side of L2 as R1. It's both those. So the only points that are included both, the only points that are both red and green are the ones in here, not including the actual ray.
Right.
This ray doesn't include any of the red points. This ray doesn't include any of the green points. We're only counting where it's both red and green. So that's the interior. That's the definition of the interior of an angle.
Okay.
One of the harder definitions for this section.
Yes.
Trying to remember the last thing we proved. I think the last one was that we proved if we have some angle and we have a line segment in there.
The last thing we did was theorem 3-4. If PQ.
PQ lie on the interior of angles.
So if P and Q are inside the interior of some angle, then the line segment PQ also lies entirely in that angle.
Right.
Right?
Yeah.
How did we prove this? We proved it by way of contradiction. We said, let A be any point between P and Q, and let's assume it's not in the interior of the angle. Now, if A is not in the interior of the angle, then A either has to be on the opposite side of this line or on the opposite side of this line as P and Q.
Right.
If it's not in the interior, which is impossible. Proof by contradiction. So we said assume by way of contradiction it's possible for A to be outside this thing, like that.
Doesn't work because then the line intersects another line twice.
Right, so then we know that A is between P and Q, so they all lie on the same line. So this, whatever this is a line. But then this line intersects this line twice, which is impossible. So that's how we know that picture's impossible. It's not because, oh, you drew something that curved. No, pictures lie. The reason we know that's impossible is because we're calling this a line, we're calling this a line, and they intersect twice.
Right.
Can't happen. I think that was like the first theorem we proved.
I think it was.
Okay, so now we're on to our next theorem. Theorem 3-5. I thought we were on 3-6. Okay, so 3-5. So what does theorem 3-5 say? So theorem 3-5 is if P is in the interior of angle O and Q is in the exterior, then, oh no, I keep going to 3-6, 3-5. If R1 and R2 are the rays of angle O, so if R1 and R2 are the rays of some angle, called angle O. You remember that notation? The angle O notation?
Yeah.
And R is a different ray. And R is a different ray also from O. Then the ray is going to be entirely in the interior of angle O or in its exterior.
What does it mean different ray from O? So O is the point, not a ray.
O is an angle.
Then the ray will lie entirely in the interior of angle O, except the point O itself, or the exterior. Oh, no, whatever. If I didn't do anything else, okay. Let's draw a picture of this really quick so you can understand what we're talking about. So we've got some angle O here. Maybe we'll do our standard lines. We've got, this is the point O. We've got R1, and we'll call this line L1. And we've got R2, and we'll call this line here L2. And we've got some other ray different from R1 and R2. Draw some other ray. I'm going to draw two potential rays. We'll do one green, one red for each case. So we could draw a ray different from these two. I could draw a ray like this, or a ray R could be something like that. Or, I guess I can just keep using red. Our ray R could be something like this.
Right.
It's just some different ray also coming from the point O. So here's the point O. Draw some ray from the point O. However you want, doesn't matter. It just has to be different from R1 and R2. So you can't draw it exactly on R1 or exactly on R2.
Which means it'll be in the interior or exterior of angle O.
With the exception of the point O itself.
Right.
Because the actual point O is not in the interior.
Okay.
Right? So let's say that picture in words really quick. So let R1 and R2 be the sides of angle O, let L1 and L2 be the lines containing them. Comma, and let R be any different ray from O, from the point O.
So, if the point R, if the ray R was right on top of R1, it wouldn't be considered its own ray, right?
Yeah, then it wouldn't be a different ray. So we're assuming R is not exactly one of those. Okay, so now notice how R can still land exactly on line 1 or line 2 going the other way.
Right.
So, 2. If R lies on L1 or L2, comma, then it's in the exterior. How do we know that? So if R happens to lie exactly on that line, how do we know it's in the exterior? Because the interior of the angle is defined as being on the same side of both lines. If it lies exactly on one of the lines, it can't be on a side of it because it's on the line. So it can't be in the interior, and so it has to be a point in the exterior. So if R lies exactly on L1, notice it can't lie up here. We said, by definition, R is something different from this ray and this ray. But it still could land exactly on L1 or exactly on L2.
Right, it could be a straight angle with R1 or R2.
Right, it could make a straight angle with R1 or R2 if you consider that an angle. Correct. Okay, so we took care of that case. Otherwise, if it's not exactly, if the ray is not exactly on one of the lines, then what? It has to be on the side of one of the lines.
Right.
So otherwise, the ray R has to be on a particular side of each line. Every point in the ray now lies on exactly the same side of each line. How do I justify that?
Well,
let's think for a second about our definition of a ray again. What exactly is the definition of a ray? So we start out with, don't read it to me, think it through. We start out with some line and a point on the line, right?
right.
Call that the point O if we're doing a ray from the point O.
Okay.
So what is the ray?
It's something that goes off of that point.
It goes off of that point. Describe, so let's take the ray to the right, like I think you're trying to say here. So you're thinking like a ray like that, right? Describe these points to me. What are these points?
They're the exact same. What would they be? Wait.
What is the difference between the points over here, here's a point A, and the points over here, here's a point A prime? How do I know A is on the ray, but A prime isn't? What are these points?
They're on the ray because it's the way the ray's going.
Well, we're trying to define the ray. The ray is all these points, so now tell me what these points are.
They're all on one side of it.
They're all on one side of what?
The point O.
Of the point O. So, the way we create a definition is we said, pick a point O on some line, pick some other line that intersects up. Doesn't matter the angle you use. There's some other line that intersects up. Then a ray is a point O together with all the points on a particular side of a line. We have a definition for what it means for 2 points to be on the same side of a line or different sides of the line. So by definition, so how do I know A and B are in the ray O? They're on the same side of this line. We'll call this line right here L prime. They're on the same side of L prime as each other. So they're both in the ray. How do I know that this isn't? Because it's on an opposite side from those points. So you take all the points on the same side of a line through the origin, and that gives you a particular ray.
Okay.
So notice that by definition, a ray takes all the points on a particular side of a line. Right?
Yeah.
So when I draw this ray, here's a ray R1 coming from O.
Yeah.
L2 goes through O.
Right.
So I can think about R as being all the points on this line. We'll say that the line that R is on we'll call just L prime. Or maybe just L, we haven't used L. So L will always be the line that R is on. By definition, all the points on R are on a particular side of the line through O.
Right.
Yeah.
So all the points on R have to be on the same side.
Okay.
So otherwise, the ray R has to be on a particular side of each line. How do I know that? Since, maybe do this one line at a time. Otherwise, the R has to be on a particular side of L1, since L1 intersects O. So since L1 intersects O, here's L1, then R can be thought of as all the points on this side of, all the points on this line on this side of L1.
Yeah.
It doesn't matter the line I use when I'm defining a ray.
Right.
So all I need is some line that goes through its starting point. Notice L1 goes through its starting point.
Yep.
So here's the line L containing R.
Why didn't you just use point O?
Point O.
You could have.
We are using point O. So otherwise the ray R has to be on a particular side of L1 since L1 intersects O.
He's saying, why do you have to use L1? Why can't you say on a particular side of point O?
Yeah.
I'm trying to argue that this thing's either in the interior or the exterior. What is the interior? It's all the points on a particular side of L1 and L2.
Oh, right.
So I need to talk about this ray now in terms of being on a particular side of L1 and L2. So now, otherwise, R has to be on a particular side of L1 since L1 intersects O. So I know whatever this ray R is, since it doesn't lie on the line L1, it has to be entirely on one side or the other. Because the way we define a ray is all the points on a line on a given side of a line that intersects O. How do we define a ray? So we've got L here, some line. How do we define a ray at O, like that? That's all the points on a particular side of a line that intersects O. So if I call a line that intersects O, L1, by definition, our ray R is all the points on L on this side of L1.
Okay.
Now maybe R happened to be up here, but no matter what, R is on a particular side of L1. And whatever side, the important point here is that R can't somehow go like this. I can't have some of my points on one side of L1 and some of my points on the other side of L1.
Right. That's not how it works.
If some of my points are on one side of L1, all of my points are on that side of L1. Right?
Right.
So, otherwise, the ray R has to be on a particular side of L1, since L1 intersects O. And also has to be on a particular side of L2. For the same reason. Of L2, since L2 intersects O. if R happens to be on the same side of L1 as R2, and the same side of L2 as R1, same side of L2 as R1, comma, then it's in the interior. Comma, kind of a long sentence, otherwise it's in the exterior. And we're done. So either it lies completely in the interior, with the exception of the point O itself, or it lies completely in the exterior. That one makes sense?
I think so.
What do you mean for, the same side of L2 is L3 or L1? Or L2, R3. Yeah. L2 is R,
What line are you reading?
the second.
The second one?
The same side of L2 is R, I don't know what that number is, right? Then it's in the interior, otherwise it's in the exterior. 4, it's on 4, sorry.
R1.
Okay.
That's R.
If R happens to be on the same side of L1 as R2, and on the same side of L2 as R1,
Okay, there you go, thank you. That's what I needed to know, is if it was R1 or R2, or R3, because it looks like a 3 now. Just because I'm kind of blind.
ha,
Talking about the comma.
okay, so you were just flat out saying my handwriting's bad. Okay.
Yeah, pretty much. So.
Any other questions on it? Well, we all have different eyes.
True.
I don't know if moving it a couple feet helps you. Feel free to move your desk wherever you want.
No, I just didn't know it was a comma or not. I didn't know that was a comma, it was like 3.
What?
Just fun.
Oh, the one and then the comma.
Yeah, it's
I
kind
see.
of confusing, because.
I see what you're saying. Good?
Yep.
I'm not gonna try using the chalkboard anymore. It's too garbage, so. I'm just gonna have to fill up and erase, fill up and erase. Okay, so now we get to theorem 3.6, far and away the hardest theorem of the section. And the author doesn't really prove the full thing. He leaves a bunch to his homework problems. I hate when authors leave theorems as homework problems, so I'm gonna do the full thing. Or at least talk you through the full thing, make sure you understand it. If P is in the interior of angle O and Q is in the exterior, then PQ in, okay. So, if P is in the interior of angle O, and Q is in the exterior, comma, then the line segment, PQ, remember when you see 2 points listed together like that, it's understood it's a line segment. Then PQ intersects angle O. So let's get this picture. Pretty close to our same standard picture that we have for all these. So P is here. All right,
And Q would be on the exterior.
right. So P's on the interior, Q's somewhere on the exterior.
Right.
Now notice that there's kind of 5 cases that we need to handle. Q could potentially be up here. Any point over here is logically equivalent, right?
Right.
It could be exactly on this line, which we'll call Q2. It could be down here, which we'll call Q3. It could be exactly on this line, which we call Q4, or it could be over here, which we call Q5. Those are the 5 cases that we need to handle. You with me?
Yes.
Now notice that there really isn't a difference between handling case Q1 and Q5.
Right.
These are both cases where the point is on the same side of one line, but the opposite side of another. In other words, if I recall this line, if I relabel this R2 and L2 and this R1 and L1, then now Q1's in the same position as Q5. So Q1 and Q5 are really the same case, so we just need to worry about Q1. And similarly, Q4 and Q2 are really the same case. That's when it's on the opposite side from P as one line, but lies directly on another line. So Q4 and Q2 are actually the same case. And so we're left with these 3 cases. Either Q is on the opposite side of one of the lines, but the same side of another one. So it's on the same side of one of the lines as P, but on the opposite side of one of the lines as P. Or Q is on the opposite side of one of the lines as P, but lies on one of the other lines. Or Q is on the opposite side of both lines as P.
Right.
Those are the 3 cases that we're going to handle. And that handles all the cases. That make sense?
Yes.
Yes.
Okay. So, set up our picture here. 1. Let R1, comma, R2 be the sides of angle O, comma, of angle O, how do I want to say it? Contained by, is that how I normally say it? Contained by,
What was that one? Oh,
contained by L1 and L2. Just trying to describe the picture we have here. So I've got my angle O, which is right here. Its sides are R1 and R2, and they lie on line 1 and line 2. Okay. 2. Let P be in the interior of angle O, comma, and Q in the exterior. Then we have 3 cases for Q. Now I'm not going to describe what those are, but we'll represent with the points Q1, Q2, and Q3. I don't want to write out what they are, but what are they? Just saying it in words so that you know the words that you'd actually write. I just don't want to write them all. Either Q1 is on the same side of one of the lines as P, but on the opposite side of the other, or Q is on the same side, or Q is on the opposite side of one line as P, but lies on one of the other lines, or Q is on the opposite side of both lines as P. That's why we'll have written out there. But that's a lot of words, and I don't want to take up all our space. And so we'll represent each case with Q1, Q2, and Q3.
Right.
So, in the case of Q1, what do we notice? So let's pretend it's right here. What do we know about Q1 relative to P?
They're on the same side of one line and opposite of the other.
They're on the same side of one line, but opposite sides of the other. So, in the case of Q1, comma, I won't say I know. In the case of Q1, P and Q1 lie on opposite sides of, which line do they lie on opposite sides of?
R1.
L1. the line L1. We don't know that they're on opposite sides of the array. We're going to have to argue that. We know that they're on opposite sides of the line L1.
Okay.
So, in the case of Q1P, Q1 lies on the opposite side of L1 as P, comma, and so, what letter should we use for our intersection point? A. And so there exists some point A
That doesn't make sense. In the
L1
case of Q1, P and Q lie on opposite sides of L as P.
of L1 as, oh, thank you. It's the as P, but yeah, the Q and Q lie on opposite sides. Thank you. Yeah, that was terrible English. So in the case of Q1, P and Q1 lie on opposite sides of L1, comma, and so PQ intersects L1 at some point. You care what we call the point? A. Took too long. So I know there's some point A on L1 between Q1 and P. Q1 and P are on opposite sides of L1, so there has to be a point on L1 between them. So there has to be some point on L1 between them, call it A.
It's not, wait, that's between what?
Yeah, okay. So you know that A should lie somewhere like right there, right?
Yeah.
Right.
But how do I know it's impossible for A to actually be down here?
Because it would intersect.
Because it can't
line
intersect twice.
More than once.
It would intersect what line more than once?
L2.
L2.
L2. So that's exactly what I'm going to argue. I'm going to say, assume by way of contradiction that A does not lie on R1. And I'm going to show that leads to us intersecting line 2 twice.
Okay.
Right? And so it has to lie on R1. What am I trying to say? I'm trying to say, in the case of Q1, the line segment PQ intersects our angle. What does it mean to intersect our angle? It means it intersects one of the rays. That's what it means to intersect our angle.
Intersect one of the rays of the point.
So my whole goal now is to argue that this point A lies on ray R1. I already know it lies somewhere on L1. I need to argue it lies on R1. The way I'm going to do that is show it's impossible for it to not lie on R1.
Right.
Okay. So 5.
B1.
Assume, by way of contradiction, that A does not lie on R1, which gives me that A is on the opposite side of L2 as Q1. Because, by definition, Q1 is on the same side of L2 as R1. Q1 was the point in the exterior that's on the same side of L2 as R1. We didn't write that out explicitly up there for the sake of saving space, but that's what Q1 is by definition, the point we chose. I'm just representing it pictorially. So assume by way of contradiction that A does not lie on R1, then that gives me that A is not on the same side of L2 as R1. So it has to be on that other side.
Right.
Comma. And so A is on the opposite side of L2 as Q1 and the opposite side of P, because P and Q1 are on the same side of L2.
Right.
So if A is on the opposite side of L2, if A is on the opposite side of L2 as Q1, then what do I know?
It intersects L2 twice.
Q1A intersects L2.
Right.
Similarly, since A is on the opposite side of L2 as P, then AP intersects L2.
Thus, QAP intersects
Yeah.
L2 twice.
So 6. Then there exist 2 points. I'll call them B and B prime. B comma B prime in L2. In L2, such that Q1 Q1 B A and A B prime P.
So that's saying then for every B.
So that's saying since A is on the opposite side of the line as Q1, then this segment has to intersect L1 at some point. We're calling that point B. And since A is on the opposite side of L2 as P, then AP has to intersect line L2 at some other point, call it B prime.
That intersects the line twice, right?
That's our contradiction.
What is that between B prime and L2 on your bracket? What does that sign?
Oh, this one?
Yeah.
That's the in. Remember when we were doing set theory? Because a line is just a set of points. So, drawing it big, it's a Greek epsilon, like that. And that says it is in. So, then there exists B and B prime in L2. Just how you read that. Such that B is between Q1 and A, and B prime is between A and P. Which gives me that Q1P intersects L2 twice. Contradiction. So then
What?
A lies on R1. Okay. You're saying what to which part?
Okay, let me just finish writing this and then I'll ask.
You guys, you have these theorems in your book. You don't need to rewrite them out verbatim.
Better.
But I just want you to understand the theorems.
Oh,
But if it
yeah,
helps, it helps.
okay.
Huh?
We do have the theorems in our book.
For the most part. Occasionally an author doesn't completely prove all of one of them. But you also have all the theorems proofs recorded. If you need it. I don't know. Feel free to write it if it helps you, but just saying. And A lies on R1.
Okay,
Right. What do you not understand?
so I'm just,
So Q1 and A were on opposite sides of L2.
yeah,
So they intersect at B. They intersect L2 at B.
I'm making,
Well, so far we're fine.
oh yeah.
A and P are on opposite sides of L2. So they have to intersect L2 at some other point B prime.
Yeah.
So now this is all one line segment.
So it can't lag.
So the line segment Q1P intersects L2 twice. Here's the line segment Q1P.
Yeah.
All these points have to be on the line segment because that point was between those two, that point was between those two, and that point was between these two. So all these points are collinear because they're all between each other. So I've got the line segment Q1P intersecting the line L2 twice. Impossible. So A must have been on R1.
What if A lies on R2?
So by definition, Q1 was on the same side of L2 as R1. We chose Q1.
Oh, okay. Yeah, I got you.
So we only knew that Q1 and P, if you look at the line segment, we only knew it intersected line L1 somewhere. We have no clue how much it intersects line 2. We know that this point A has to lie on L1. We assume by way of contradiction that the point A wasn't also on R1. We assumed then it was a point down here. That was impossible. So the point where Q1P intersects the line L1 has to be on R1. And so it intersects the angle.
Wait, so we were trying to prove,
PQ intersects angle O. Okay. That's ultimately what we were trying to show. We're trying to show PQ intersects angle O. From the start. If P's in the interior of angle O and Q's in the exterior, then PQ intersects angle O.
but point A can lie on R2.
No.
Why not?
So
Just said-
point, oh, it could have been somewhere, here's what we know about A. A has to be on L1. By definition, A is the point on L1 between Q1 and P. I know Q1 and P are on opposite sides of L1, so A is a point somewhere on L1 between Q1 and P. Maybe it's up here, maybe it's down here, I don't know, but we're on L1 for sure. If it was on L1 and on L2, then it would be the point O, because those two lines only intersect at one point.
Well, nowhere, where does it say that A has to lie on L1?
We proved that.
So Q1 and P lie on opposite sides of L1,
Which means they
but the
intersect
same
on-
side of L2.
Where does it say that?
Well, I told you I wasn't going to write it all out. Then we have three cases for Q, ... I may explain with the picture, Q1, Q2, Q3.
Yeah.
So Q1 is on the same side of L2 as P, and is on the opposite side of L1 as P. That's the case we're handling right now. We're going to handle each case.
Wow, okay.
So we're handling the case of Q1.
Yeah.
That's it so far, right?
Oh, okay.
So in the case of Q1, then A is the point on L1 between Q1 and P. We showed A can't be down here, and so it has to be up here. And so it's on R1. That's our logic so far with that. Good?
Yeah.
Okay. So then the next case. So probably easier to redraw it. So we've got, I think we were calling this one L1
Yeah.
and this one L2. Try and be consistent. Here's O. Here's R2. Here's R1. We've got P somewhere in the interior. And now our Q, which we're representing with Q2, is going to be on the opposite side of one of the lines as P, and then on the other line, actually lie on the other line. You with me?
Mm-hmm.
So Q2 is either right here or right here. These are logically equivalent cases. We're just going to handle this case. So I know that P and Q2 are on the opposite sides of one of the lines, and Q2 lies exactly on one of the other lines. Right? Okay. So 8. In the case of Q2, I know that P and Q2 are on opposite sides of what?
Line.
P and Q2 are on opposite sides of L1, and so intersect it. And so there exists a point on L1 between them. And so there exists, what did we call the point before? Is that what we used A for? And so there exists A in, which line are we talking about? Opposite sides of L1. So there exists A in L1 such that A is between them. So such that Q2, A, P. So if P and Q2 are on opposite sides of L1, there has to exist some point A on L1 between them. And either A is a part of the ray, or A isn't. So those are our two options for A so far. We just show that one's impossible, and so it has to be the other. You with me so far?
But won't that, well, when you connect both of those, won't they intersect P? I mean, won't they intersect a line twice?
That's exactly where our contradiction is going to be. So we know that the good point is actually A, right here, right?
Right.
This is the bad point. So we're going to show that this is impossible. We're going to assume A's down here and show that leads to contradiction. So if A's down here, then what are we going to have? We're going to have this line segment right here, and then connect like this. And so this is going to intersect at some point B.
Well, Q can be on the other line too, right?
We're just handling one case at a time. Look, once we do one proof, just relabel everything and you reprove the other proof. Call your L2 L1 instead, and call your L1 L2 instead. Okay, you handled the other line. So it doesn't matter if Q's on this line or this line, they're the same thing. You said Q is on L2, couldn't have been on L1, relabel it. Okay, now it's on L2 again. If I say Q's down here, I can just call this line L2, this line L1, and this R2 and this R1, and it doesn't change anything. P's still in the interior. So it's just a relabeling thing. It's like you're flipping your picture.
Okay.
Doesn't change anything, right?
Yeah.
So all we care about is Q is on one of the lines and on the opposite side of another one of the lines. So we're calling the line that Q's on L2, and we're calling the line that they're on opposite sides of L1. Okay, so we have the segment now, Q2P. And what's wrong with this segment Q2P?
It intersects L2 twice.
Intersects. Yep.
It intersects L2 twice. Perfect. So that's going to be our contradiction. Okay, so 9. Assume, by way of contradiction, that A is not in R1. So if it's not in R1, then what does that mean? It means it has to be on the opposite side of L2 as P. So then A is on the opposite side of L2 as P, which gives me that there exists some point B in L2 such that ABP. So let's follow the logic there. Assume by way of contradiction that A is not in R1. So I know A is a point on L1, and it's not on R1. By definition, R1 is all the points on this side of L2. So if A is not in R1, A cannot be on this side of L2. So it has to be on the opposite side of L2 as P. So then A is on the opposite side of L2 as P. Now if P and A are on opposite sides of L2, then there has to be a point B on L2 between them. So that gives me that there exists, that's my backwards E, sorry, not like softball. That gives me that there exists B in L2 such that B is between A and P. So 10. Then the segment Q2 to P intersects L2 at Q2 and B. Contradiction. Right?
Yeah.
Because Q2 is already a point on L2, and so the segment Q2 to P is intersecting L2 twice. Contradiction, which gives me, therefore, A is in R1, which gives me the segment Q2P intersects the angle O.
Wait, so, a line can intersect as many lines as you want, but it can't intersect the same line twice.
Exactly. And intuitively, you kind of know that. If I have some line, how many lines can I draw that intersect that? Infinite. So yeah, one line can intersect infinitely many lines.
Okay.
Okay. So we handled that case. Any questions on that case?
I think so.
Okay. So now let's draw the picture for our last case and go through that. So once again, we've got some line. We were calling this one L1. We've got some other line. We were calling this L2. They intersect at some O. This is R1. And this is R2. And we got P somewhere in the interior. And now we're handling Q3. The point is out here. Right? Let me draw that down here so we can draw lines above it. Here's our point Q sub 3. Okay, so what do I know about Q sub 3 and P?
They're both on opposite sides of the
They're on opposite sides of both lines. Right?
The only place they can intersect is angle O.
No. Let me help your intuition a little bit. P could be right here.
Oh yeah, you're right.
Q3 could be right here. Okay. So definitely don't necessarily intersect at angle O.
But they have to intersect at angle R1.
They have to intersect
At R1 or R2.
at R1. Yeah, I could just as easily draw the point down here, that point over here. In that case,
Right.
they're intersecting at R2.
They intersect L2 and R1.
So, 11. In the case of Q3, comma, P and Q3 are on opposite sides of, which line do I want to say first? L2, which gives me that there exists some point, I'm going to call it Q2, and you'll see why here in a second. There exists some point Q2 in L2, such that Q3, Q2, P. So, since Q3 and P are on opposite sides of L2, then there has to be some point on L2 between them, right? And I'm going to call the point between them Q2. So the point between them could be like that, but what if these points happen to be clear down here? Then the point Q2 could have been right there. So here's our two options for the point Q2. Let's do it in red to remind us that these are choices. We got to choose one or the other. Since P and Q3 are on opposite sides of L2, there has to be some point on L2 between them.
Right.
Yes.
Now, if the point, which means that the point has to either be on R2 or not on R2, right?
Yeah.
So if the point is on R2, we're done. We showed that the segment Q3P intersects the angle.
Wait, you're saying it has to be on R2? It has
No.
to intersect on R2?
It does not have to intersect on R2. It could. Imagine I drew this point right here and P right here.
It has to intersect on L2.
It has to intersect on L2. It could intersect on R2. So either our point where they intersect is on R2 or it's not. We have two potential pictures here. It could be that my points are both over here, in which case they're not going to intersect on R2. Or both my points could have been like points right here, in which case they would intersect on R2.
Right.
But it has to be one or the other. Either they intersect on R2 or they don't. If they intersect on R2, notice we're done. Then the segment intersects the angle. Because R2 is part of the angle. So 12, oops, observe that if Q2 lies on R2, comma, we're done. Right?
You just say that.
Yeah, if Q2 lies on R2, we're done. Or if Q2 lies on R2, if you don't like we're done, observe that if Q2 lies on R2, then the segment PQ3 intersects the angle. Or I think we've been doing the Q first, just for sake of consistency, doesn't matter. Then Q3P intersects angle O. Observe that if Q2 doesn't lie on R2, comma, then Q3P intersects angle O. That's an angle symbol. Intersects angle O by case 2. In other words, we've already handled this case. And so we're done. If Q2 is over here, we already showed that if Q2 is a point on the line and P is on the opposite side, then this intersects R1. That's what we did when we handled Q2. That's why I called the point Q2. To show you, if Q2 is over here, we intersect it. If Q2 is over here, we already handled that case.
Right.
That was case Q2. So we've already shown if the point's over here, then this segment intersects this, and so this segment has to, because that's between them. So we're done. We handled all the cases. So proving the last case turns out to be not that different from proving the second case. Make sense? All right, that's the big proof of that chapter. The hard one. Theorem 3.6 and exercise group 2.6. Did we already talk about the interior of an angle? Or of a triangle?
Maybe, we talked about it a little bit. Kind of talked about how it's multiple rays.
The interior of two of the angles that compose it, or all three angles. I think we did that, okay. So, I don't think I'm missing anything. Let me just look in the book. Sometimes it's clear from my notes if I'm skipping something. So, we did that, Theorem 2.6, and then it's the end. Okay, so yeah. So that ends chapter 3 material. And now we move on to chapter 4. Chapter 4 material is all about congruence. Congruence, the most important relation that we use in geometry. Now, congruence is like our most basic way of talking about size. So let's think about this for a second. How do you determine if one object is bigger than another object?
Volume.
If one object's taller than another object?
Measuring.
You measure them, right? I go, I measure you, I see which number's bigger, and that's how I know if you're taller than him or he's shorter than you. Is that how you have to do it?
No. No.
How tall is this classroom?
9 feet.
How tall is it exactly?
Not
Don't know. Neither do I. How tall am I exactly? Don't know. Neither do I. Who's taller, me or the classroom?
Classroom.
How'd you know that? You don't even know our heights.
Because you're fitting inside of it.
It's way of contrast.
What's longer, the length of this desk or the width of the Pacific Ocean?
Pacific Ocean.
The Pacific Ocean.
How do you know? You don't know the width of this desk. You don't know the width of the Pacific Ocean. So you don't need to actually know the actual measurement to determine one is taller or one is shorter. One is longer or one is shorter. One is larger or one is smaller. So assigning numbers to things, that was a revolution that happened. you can imagine going back into days when you have tribal villages, people comparing heights. And maybe someone would say, my son is this tall, and they'd have a stick for how tall their son is, or a line on the stick. This is the height of my son. They would say he's 5 foot 6 inches or whatever. That was a development to actually pick a metric and start doing it in terms of that metric. Or he might count how many of a particular stick this kid is. He's 3 of these sticks tall. And then you get your first notion of a metric. And you can go to some other village and see how many sticks their tallest guy is, if you bring that same stick with you. And so this notion of using these sticks to compare and to comparing these sticks is what congruence gets at. So let's first, we're adding an undefined term here. So our undefined term is congruent or congruence. It's a congruence relation. And we're going to be adding a new postulate group. The postulate that introduces congruence. Intuitively, what is congruent going to mean? So we're going to start by talking about congruent with line segments. So here's AB. Here's A prime, B prime. Intuitively, what it's going to mean for two segments to be congruent is they have the same length. That's intuitively what it's going to mean.
Right.
You with me?
Yeah.
Now, we don't want to confuse congruence with equality. So our symbolization here is going to be AB is congruent to A prime, B prime. They have the same length. That's how we're going to represent that from here on out. This is a notation we're going to introduce in our postulates. So our postulates will give us the rules. First, just kind of want to get you used to this for a second. So intuitively means the same length, and that's how we're going to write it. Now, why don't we just say something like this? AB is equal to A prime, B prime. Their lengths are the same. Why don't we just say that? What does this say right here versus what this says?
Top one says roughly equal to.
No, this one says they have identical lengths. That's exactly what it says. Their lengths are perfectly identical. What does this one say?
Everything's identical.
Everything. Yeah, everything.
AB and AB is equal.
Oh, it's the same line.
Yeah, this is saying these are identical segments. It's saying A and A prime are the exact same point, and B prime are the exact same point, and these are the exact same segments. Are these the exact same segments?
No.
No. So it would be very bad for me to write this. Now, it just so happens that if two segments are equal, so if AB is equal to CD, so this is also the point C, this is also the point D. We just have two names for the same point, who cares? If we have AB is equal to CD, question, is AB congruent to CD?
Yes.
No.
100%. That's the same way.
Does this line segment have the same length as this line segment?
Yes.
For sure. So they have the same length. So don't get confused between equality and congruence. If two segments are congruent, they may or may not be the same segment. But if two segments are equal, if they are the same segment, then they are congruent to each other. So being equal implies they're congruent, but being congruent does not imply they're equal. Those are two very different things. Don't mix those two up. Okay. One of our postulates, well, let's just write our first postulate. So given a point AB, let me draw it out pictorially. So here's what it's going to say. We've got some line L here, and we've got 2 points A and B. And then we've got some other line here called L prime. And we pick some point on here, A prime. Our first postulate is going to be that there exists 2 points on L prime. Sorry, this was L prime. There exists 2 points on L prime. I think the author calls them B prime and B double prime. B prime and B double prime. There exists 2 and only 2 points on L prime. Call them B prime and B double prime on opposite sides of A, such that this segment is congruent to this segment and this segment is congruent to this segment. So if I give you some segment and I give you some point on another line, and I say draw a line segment congruent to this, starting at point A. There's two you could draw. You could draw this line segment or this line segment. That's what postulate 1 is going to say. So we're on
3.
group 3. and 3, 1 is going to be, try and get the language somewhat the same, given A and B on L and a point A prime on L prime. Okay. So, given points A, B on L, and here is some of this, and A prime on L prime, comma, there are exactly 2 points on L prime such that 2 points on L prime, call them, how did I say it here? There exists 2 unique points, B prime. So there are exactly 2 points, B prime and B double prime on L prime, such that there are exactly 2 points, B prime, B double prime, B prime on either side of A prime, such that AB is congruent to A prime B prime and AB is congruent to A prime B double prime. Okay, that's what it says exactly. Yeah, I heard the fire alarm earlier. Okay, so if you are given some segment, 2 points AB on a line, and you know A prime is on some other line L prime, then there exists 2 and only 2 points on either side of A prime, 1 on each side of A prime, so 2 points total. There exists 1 point on each side of A prime, such that this segment is congruent to that and this segment is congruent to that. That's the first postulate. So it tells us how we can find, it tells us that we can find segments congruent to given segments. That's essentially what it tells us.
Okay.
Okay.
Saying there's an infinite amount of points, so there's 1 point that makes the line congruent to another line.
Right, so what was our given information that we started with? So we start with A, B, and A prime. Then we're guaranteed we can find B prime and B double prime, such that they're equidistant from A prime. Okay, our second postulate says 3-2 says that congruence is an equivalence relation. And I'll explain what that means. The author's not going to use this terminology, but equivalence relations come up so much that it's going to be important that you get it. Equivalence relations satisfy 3 properties that we call reflexive, symmetric, and transitive. So it's always the case that AB is congruent to AB if AB is congruent to CD. That implies CD is congruent to AB. And then if AB is congruent to CD and CD is congruent to EF, that implies AB is congruent to EF. We call this one the reflexive property. We call this one symmetric. We call this one transitive. Okay, so let's get intuition for an equivalence relation really quick, then come back to congruence. So a standard equivalence relation would be, well, this one's going to be basically the same thing as congruence, but we'll use that as intuition. So first off, let's think about the is the same height relation between people. So it's a relation, it takes 2 people, and it spits out true or false. Now are me and you the same height? No, so if you plug me and you into the is the same height relation, it spits out false. It's a relation. Takes two terms, spits out true or false. Congruence is a relation. Takes two line segments, spits out true or false. Right? Now property 1 says every line segment is congruent to itself. Make sense? Property 2 says if line segment AB is congruent to line segment CD, then line segment CD is congruent to line segment AB. And then finally, the last one says, if AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. If we think about this in terms of height and people, the first property says, you're the same tall as yourself. The second one says, if you're the same tall as Jack, Jack's the same tall as you. This one says, if you're the same tall as Jack and Jack's the same tall as Jill, you're the same tall as Jill.
Right.
Now there's tons of equivalence relations. So there's lots of relations out there that have these properties. Let's think about, again, on the set of all people, we'll use a relation has the same parents as. Do you always have the same parents as yourself?
Yes.
So has the same parents as is a reflexive relation. Everyone always has the same parents as himself. If you have the same parents as Jack, does Jack have the same parents as you?
Yes.
So has the same parents is symmetric. If you have the same parents as Jack and Jack has the same parents as Jill, do you have the same parents as Jill?
Yes.
So it's transitive. So if it has all three of these properties, we call it a congruence relation. So take a relation, if it has these three properties, we call it a congruence relation. An equivalence relation, sorry. Congruence is an equivalence relation. What does that mean? It's reflexive, it's symmetric, it's transitive. Has the same parents as is also an equivalence relation. The equal sign is also an equivalence relation. If is A always equal to A? If A equals B and B equals, if A equals B, does B equal A?
Yeah.
If A equals B and B equals C, does A equal C? So equals also satisfy that. Let's get an example of a relation that is not an equivalence relation to help you understand this. Let's think about the less than on the real numbers. Is a number x always less than itself?
No.
No, so it's not reflexive. If x is less than y, does that imply y is less than x?
No.
No, so it's not symmetric. If x is less than y and y is less than z, does that imply that x is less than z? Yes, in that case it is. So it's not reflexive, not symmetric, it is transitive. So the less than only has one of these three properties. You have to have all three of these properties to be considered an equivalence relation. So congruence is an equivalence relation. There's lots of equivalence relations out there. When it comes to a particular field of mathematics, it's often the case that it has its associated congruence relation that we care about. When it comes to set theory, what we care about is sets having the same size as each other. And that's a congruence relation. Does every set have the same size as itself?
Yes.
Yes. If set A has the same size as set B, does set B have the same size as set A?
Yes.
Yes. If A has the same size as B and B has the same size as C, does A have the same size as C?
Yes.
So set size is a congruence relation. And sets that satisfy this relation then have the same size or somehow equivalent. We call them isomorphic to each other in set theory. Here we're going to call things that are the same congruent to each other. It's a congruence relation we care about. If you were in my topology class, then we'd be studying homeomorphisms. We would prove that homeomorphisms are an equivalence relations, and we'd say two things are equivalent means they're homeomorphic. So in this class, we're going to call them congruent. This is the sameness relation that we care about, the congruence relation. And that's what we're going to mean by these are somehow the same, these are somehow equivalent, they're congruent. So that's the relation that we really care about for the majority of this class from here on out. This congruence relation, saying that two geometric figures are somehow the same. That's what congruence captures. Okay, so now let's get our last postulate. Last postulate 3.3. And what does this one say? It says, given A, B, C, do we put them online? Yes. Given A, B, C on L, and A prime, B prime, C prime on L prime, comma, then if 1 let me draw my picture over here to also help us see it before we continue with this. It's kind of button thin. So we have a line L, we have a line L prime. We're going to have a point A, B, C, A prime, B prime, C prime. Okay, so we're going to have these 3 points. Our first one is going to say, if I know that AB is congruent to A prime, B prime, and I know that BC is congruent to B prime, C prime, what do I know?
That A prime and C prime are the same as A and C.
Yeah, that AC is congruent to A prime, C prime. The way we sometimes say that loosely is equals added to equals are equals. So if this is congruent to this, and then we have this is congruent to this, then the whole thing is congruent to the whole thing. In other words, you take things that are congruent, add congruent things to them, and the result is congruent. So if AB is congruent to A prime, B prime, and BC is congruent to B prime, C prime, then that gives us that AC is congruent to A prime, C prime. The whole thing is congruent to the whole thing. Similarly, the next one we often talk about as equals subtracted from equals or equals. So let's think about this another way. Imagine that I told you that AC, this distance, is the same as this distance. So AC is congruent to A prime, C prime. And then this little piece, BC, is congruent to B prime, C prime. What do I know about these pieces?
They're congruent.
They're congruent. If the whole thing is congruent to the whole thing, and a piece we remove is congruent to a piece we remove, then the remaining piece is congruent to the remaining piece. The way we often say that is equals subtracted from equals results in equals. So equals added to equals or equal is the way we say the first one, and equals subtracted from equals is how we sometimes say the second one, just as a high level way of saying it. But precisely it says that if AC is congruent to A prime, C prime, and BC is congruent to B prime, C prime, then that gives me that AB is congruent to A prime, B prime. Now, if you look in your book, I think the author does, puts a little asterisk next to this one, because this actually doesn't have to be a postulate. We are actually going to be able to prove this from our given information. But it's okay to use it as a postulate for the sake of your proofs. So we'll come back and actually prove that one. It's not actually something that we have to treat as a postulate, but for now it's okay to treat as a postulate. It's convenient to treat as a postulate, let's just say. So you're going to be asked to do some homework problems where you're allowed to use this as a postulate, and then later we'll come back and prove this and we no longer have to rely on it as a postulate. It's going to be a theorem. Okay, let's get our first definition of the chapter. Now we are postulates. Such that, Okay, this is defining less than and greater than. Okay, so we know what it means for, in some sense, we have a notion for two things being congruent, but we can also have two line segments shorter than each other or two line segments taller than each other, right? When we're talking about lengths, we want to know when we compare two lengths, either they're the same or one's longer than the other and one's shorter than the other. Right?
Right.
How would, if I have this stick here, and I have this stick here, and I want to say if one's shorter than the other, how would I do that? You go stick it right next to it, right? So we make this point coincide with this point, right? And then we see where this intersects that. We mark off here the same length there, and we see if there's some left over. If there's some left over, then this one was taller than this one, and this one was smaller than this one. So that is what our definition is going to capture for lesson. And this is going to be the hard definition of this section. So, definition 4.1, tried it out. Definition 4.1. So let AB be a segment, let A prime B prime be points on L prime, and let B double prime be on the same side of. Okay. So let AB be a segment. Comma. Let A prime and B prime be points on some line L prime, comma, and let B double prime be the unique point on the same side of A prime as B prime, such that AB is congruent to A prime B double prime. Okay, let's make sense of this messy definition. So we're given a line segment AB. Here's our line segment AB. And we've got two other points on the line L prime. Call them A prime and B prime. Now I'm wondering, how does AB compare with A prime B prime? If I want to know if this is shorter than this, how do I actually do this? What's the mechanical process you go through?
Put them next to each other, see.
Right, you come, you say, let's put A here, and let's see where this B would land if we dropped it down on this line as well. Or, using our postulates, I know that here's some segment. I know that by this postulate, there has to be some point on this line I can find, on this side of this line, call it B double prime. I don't know which side of this it lies on, but there has to be some point B double prime, such that A prime B double prime is the same length as this. So exactly what you said is basically we're putting A on A prime, and then we let the B and see where the B lands. And the B is either going to land before B prime, or it's going to land directly on B prime, or it's going to come after B prime. Right? If I were to drop this down, make the A there, and then drop B here, it's either going to land before B prime, right on B prime, or after B prime. Those are our cases. You with me?
Yeah.
Okay. If it comes before B prime, that's what B double prime is. It's where this point lands. So if you force A to land on A prime, then B double prime is where B lands. Or look at up here. Let A and B be a segment, and let A prime and B prime be points on L prime. So here's A prime and B prime on L prime. And let B double prime be the unique point on the same side of A prime as B prime. So B double prime has to be over here. We're not looking for the congruent point over here. We're looking for the congruent point over here, such that AB is congruent to A prime B double prime. So we got our B double prime. So this distance has to be the same as this distance. So here's one possible picture. We'll do one possible picture at a time. In this case, if the B double prime lands between A prime and B prime, how does this segment compare with this segment? Which one's longer? when I take AB and I draw it down, then the point where B hits this line is B double prime.
A prime, B prime, so on.
A prime, B prime's longer. Because the point where this hit here, when we marked off its height, it was somewhere between those. Right? We've got our line starting at point A prime here. Here's B prime. We've got our line segment AB here. And we're saying, we're measuring you off, where do you intersect this point? Where do you intersect this line? That's B double prime. If it's between A prime and B prime, then AB is shorter than A prime, B prime. So, maybe just having it to the side there is enough. If we have let me try to make sure I don't skip any language here. So, if we have A prime, B double prime, B prime, then I have AB is less than A prime, B prime. And if we instead had A prime, B double prime, then we say AB is greater than A prime, B prime. And if B double prime is equal to B prime, if they turned out to be the same point, then AB is congruent to A prime, B prime. So there's our definition of greater than, less than, greater than, or less than. So over here I have the case drawn out where AB is obviously less than A prime, B prime. How do you know AB is less than A prime, B prime? When we line it up and we mark it off, B double prime was between A prime and B prime. So if it turns out it went A prime, B double prime, B prime, so B double prime was between A prime and B prime, then that meant that AB was smaller than A prime, B prime. If we would have had the case, so I'll draw out the second case, if it would have been like this, here's our segment AB, here's our line, here's A prime, here's B prime. When I could line them up and I find where B would hit this line over here at B double prime, this was a case where AB is bigger than A prime, B prime. And how do we know? Because it goes A prime, B double prime now. So B prime is the middle point. So, if it goes A prime, B double prime, then that must mean AB is greater than A prime, B prime. You guys dying on me?
Yes.
We can't survive?
No.
Sometimes, oh yeah,
Sorry.
sorry, I'm understanding, yes,
But you're dying on me?
yeah.
Well, no point pushing too far if you're gonna die on me.
All right.
We just got the definitions. Theorem 4.1 we basically get for free.
With your little thing tonight, I think we can move it to Monday night this week, because Brother Coley has his class.
What class?
What class?
Little thing. A UO class.
On Monday night? Oh, Tuesday night. Oh, I see what you're saying. Yeah. Next week, Monday night, will you guys actually show up?
How about we just, why do we have to move it?
Because there's a meeting.
Because UO meeting
Yeah, it comes once a month. So,
starts at 7:30.
yeah. So, we can do Monday night, that's fine by me. So, Monday night next week.
Okay.
Right? So, the day before class.
Mm-hmm.
Okay. Alright. We're so close. We got 3 theorems to get through, and then we're done. That might be a lot for you guys.
We should go out and walk around the building or something.
Well,
Wait,
I guess we'll call it there. We still have a bit of homework to go over, don't we?
Yes.
Okay, so yeah, we'll end it there. So we introduced 3 new postulates and one new definition for what it meant to be greater than, less than. So let's have you go through, do at least the first exercise, or I think the first exercise group is just a skip one. It just says like, do these things, or say these things in your own words.
We still got to do 3 to 6 as well.
So 4-1, don't worry about, but do exercise group 4-2. Make sure you do 4-2.
Don't worry about exercise group 4-1.
4-1 is just 2 problems that says restate this in your own words. And so
So just skip 4-1.
you can always skip those types of problems. So you can skip 4-1. Make sure you do exercise group 4-2. And I think that'll help this definition sink in and these postulates sink in. And then maybe it'll be a lot easier when you're more comfortable with these. So yeah, we can call it there for now.
Okay, so next time, check.
What's the number?
Next time we have 3, 6, and 4, 2.
From